Well, good day, everybody. I hope everyone's enjoying their 2014 Thanksgiving. And with all this food being cooked up, I couldn't help but think about all of the everyday applications that people use of thermodynamics they don't even realize. And one application that people don't realize, and if you do take thermodynamics in college, you'll be seeing a lot of problems that are somewhat related to this, a common household pot. And let's say that we fill the pot with water, put it on the stove, and for safety reasons, I'm not using real life oven stove. That's one, and then two, because it's Thanksgiving, the kitchen's already been taken up with people cooking good stuff. So don't want to inhibit that. But let's say that, let's use our imagination, we put water in it, and we have heat going in at the bottom, so it's entering the system, and we have a lid. Well, when you do take thermodynamics, you will find out that there's a problem similar to this, but it'll be a piston problem more than likely. In the same way, you have the weight of the lid pressing down, you have heat entering the system above, the water absorbing the heat, and then eventually the water will turn into steam, and then the steam and the pressure will equal and will lift up. Now, that's one way of an everyday thermodynamics problem that you can make more complicated by using equations, which actually aren't that complicated once you get used to them. But there is an even better example of everyday thermodynamics. Well, and with this example, because of the ideal gas law, and we're currently in Oklahoma, which we're not too high above sea level, which at sea level the boiling point of water is 212 degrees Fahrenheit or 100 degrees Celsius approximately. And of course, as elevation increases, atmospheric pressure decreases, which if atmospheric pressure decreases according to the ideal gas law of PV equals nRT, the boiling point of water increases. And if you're a cook, that would actually increase the cooking time of most things. And so to solve that problem, we have another example of everyday thermodynamics, which I kind of took this from my aunt after I turned it back quickly, is this pressure cooker. And so with a pressure cooker, basically the same concept, but the thing is that this lid is locked in place. We have a fixed volume, and with a fixed volume, the boiling point of water increases to approximately 250 degrees Fahrenheit from 212 degrees Fahrenheit. And why would this matter, you would ask? Well, if that's the case, if you look at a PV diagram, even though, since the volume remains the same, and if you have another thermodynamics problem, this would be a contained fixed volume, and so therefore pressure would increase, but volume would remain the same. And on the PV diagram, the line actually represents temperature. Temperature increases. And so because of that, because of this thing right here, it cooks things a lot faster because of higher temperatures. And since, like for a roast, for example, it takes about approximately 30% lesser time than it would normally, because since the pressure is built up in there, pressure is uniformly surrounding the object, the thing that you're wanting to cook, and so it penetrates it quicker. And so the energy from the steam is transferred into the energy of the water molecules that are contained inside the food. And because of that, a lot of scientists say that it's about 50% to 75% more effective and more efficient than cooking with regular material, because you use less energy, if you're using an electric stove, less electricity, and if you're using a gas stove, less gas. And it's also effective for those people who live at higher temperatures because it has the same effect because you control the atmospheric pressure inside. The pressure cooker has been around, the concept has been around since about the 17th century when a physicist introduced it, and it became modernized in about the early 1900s. The idea did. And it's kind of gotten a bad rap because of, in the early days of, explosions, because obviously if you put something under an immense amount of pressure and you don't have a correct safety valve, then, it's going to find a way out. Every material has a breaking point. And so this is another way of having engineering problems. It's basically all engineering is applied sciences. It's saying here's a law and how do we make that into something that we can use in everyday life. And a pressure cooker is a perfect example of that. Just using PV equals nRT. P being pressure, V being volume, N being the number of moles, R is a gas constant, and T is temperature. And so since volume is fixed and pressure increases, and obviously the number of moles and R is constant, the only thing that can increase, if you write the equation down, PV equals nRT. And so if you have pressure increasing, but volume is fixed, and these two are constant because they don't change, the only thing that can increase to make this even out is temperature. So there you go. There is the everyday example of thermodynamics and physics in your everyday life that you weren't even aware of.